we are going to take the second lecture from Dr. Mayowa, Kolade. And I know it's a very workshop where we learn what we want from, but at the same time we see Dr. Kolade to talk to us. Thank you, sir.
Good afternoon, sirs and as I start with existing, existing. So I started existing protocol now to say very big thank you to the organizers for Solidity, Dr. Ogunjobi for the privilege to share with us. And a special thanks to Prof. Franklin and Professor Sherika for the very robust previous session. My job this afternoon is very, very simple. It's to create a bridge. I'm in the room with very, very smart people. I was saying to our clinical team or resident doctors sometime back that I think radiologists are perhaps one of the people who very significantly move the field of nuclear for. And chemistry has a bit of chemistry in it, it's about physics in it, a bit of many other things in it. So I'm seeing people here who understand structures, and when I was in UI, chemistry, one person used to make something fast. Something is very smart. But you see, the issue is that you spend most of your day thinking about structures like this. I spend most of my day thinking about how to find diseases in patients and how to utilize that information to get remarkable outcomes. But this is where the problem usually is that you probably don't see how impactful what you do is or I probably don't see how impactful what it is you do can translate to what I can. So that's why I have remixed my topic and I want to make it combo. So I'm calling it the journey from your molecule to my patient's clinical period. So from molecule to so we're talking about radioligand, how radioligand help in diagnosis and therapy. So first of all, why is that really important? Because I'm sure I can have a very strong guess that 99% of people in this group who have had some medical picture taken before have not had to have radioligand imaging done. It's more the theoretical concept. The majority of us do. If you had a chest X-ray before, can you wave your hands? Okay. If you had an ultrasound, can you wave your hands? If you had a CT, don't raise your hand. If you thought you had a CT, it's just for your privacy sake, okay? So you had imaging done before. But all of those images you had taken were essentially images of structure, bodily structure. That's simply an anatomy. And in certain cases, anatomy is great, but anatomy is not enough. You can think about it this way. You had a very powerful drone. You all know about drones. Drones, you see them in weddings these days, flying around, taking pictures. So I was to give you a drone to fight above UI. UI is feeling about, so your drone is very, very, very powerful and fly high. And I thought that there's a fire in UI. There's a fire in one of the rooms in UI. With your drone, tell me where the fire is. So you'll be able to. Sorry for the.
Done. Right. So with that drone, before that drone can pick where the fire is burning, the fire will have to burn in the room first and probably start burning the roof before you can pick it from the drone. That's what anatomical imaging is. Anatomical imaging looks at structure, but structure many times can look normal, even though there's a fire burning inside the building. Until it burns to a certain extent, you won't be able to tell it from outside. So anatomical imaging like this CT here, relies on the shape. Now, those three images, and I'm not trying to get you to make a diagnosis from those images, but they all look gray and the same. Whereas what molecular imaging does, which is nuclear medicine essentially, is that it relies on being able to see the fire that is burning inside the building. So that way we can pick up issues faster We can tell fire service where to go quickly to put it off, even though it hasn't burned the roof yet. If it's burning the roof, the building is already gone. It's probably too late. So we are able to bypass the limitations of late diagnosis. We're able to bypass the limitations of waiting for the disease to be quite advanced before we step in. But with molecular imaging, see what your molecules can help us do. Your molecules help us to fish out parts that may have looked normal on structural imaging. You can see those very red, glowing, bright dots there. The images on the left and right are identical. But now we can move quicker. Now we can pick up things at a smaller and a more, at an earlier stage. And that's how we can change the clinical outcomes for patients. This molecule that's used here is what Prof spoke about, FDG. That's simply glucose water, but glucose water with a tracker in it. So we can track around your body and see what is consuming more glucose than it should. And that will be an area to be suspicious of. But because of the great work that you chemists and radiochemists and the pharmacists are doing, we've been able to move past just looking at glucose to looking at specific receptors. Now, the issue with glucose imaging is that whilst it's great, it is very sensitive, but it's not very specific, meaning that it picks up what we want and sometimes what we don't want. And we've been able to move past that to specific receptors now that are very peculiar to the disease type we want to look at. And we have great images like this. Now, all of this I've said is probably Greek to someone. And I want, yes, okay. So I want to bring it down. Look at these two beautiful vehicles on your screen. They're almost square-shaped. I know the one you prefer. So for Prof, there is we have this very bright yellow buses. You may have seen them in Lagos on your way from the airport to Ibadan. They are world class. They have a global reputation. One of the things that they are very good at doing is that they don't have an upper limit. 18-seater bus, downfall? No way. You pack 18, you pack more. Like the image you can see, you can even pack on top. I want you to think of this as FDG. FDG picks up what you want it to pick up, including what you don't want it to pick up. So essentially, it can pick up a lot of stuff as it goes along the way. But the problem is that when it's in the setting of cancer, it picks up the cancer cell, which eats up a lot of glucose. It also picks up TB, which is not too rare in our environment. It also picks up infection, which is not too rare in our environment. So it's like the downfall. However, this next vehicle, name the governor of your state, who is using this one with his convoy. If with the downfall, all you need to do is wave or flag. Even if you don't, the downfall will park and ask you to get here. But this one, wave from now to next year. It has a destination it's going to. It will go past infection. It will go past TB. It will go past trauma. And it will only park at the destination where this VIP is intended for. This is receptor imaging. And we're able to do this because of the molecules we create. So thank you for doing what you do. And this is a good junction to say that many of these things we're talking about here are not theoretical. These are scans and studies that we are doing at the University College Hospital with the very brilliant men and women who are in this room. I can mention name after name, after name, after name, after name, after name. So these things are happening in Nigeria. And it's thanks to the very foundational work that you scientists are doing. And now, because we have these amazing targets, we're able not just to see problems, we're able to go after them with remarkable precision. You remember when I was talking about the drone? And this special drone now doesn't just see roofs, but in a sense can remove the roof to see inside, to see where the fire is burning. Because of that, your fire brigade doesn't need to start going around from I almost said 8 weeks, from Kuti to Melambi to Teda to Indie Hall, looking for the pot of beans that is burning. We already know where that pot of beans must be burning. It must be Indie Hall. So because of this remarkable precision that we have, we're able to reach things with remarkable precision as well. The concept of the magic bullet was popularized in the early 1900s by this man called Paul Ehrlich. What is said is that he created the idea of the magic bullet. But I'm very careful about these things these days, because in primary school I was told that Mungo Park discovered the River Niger. But when he discovered it, there were people probably swimming in River Niger already, so he didn't really discover it. So I'll just say that this man probably popularized this concept. And Paul Ehrlich's concept was that with a magic bullet, we could treat a disease in a patient without treating the patient. Now that's a bit outlandish, right? Where you want to kill a problem in a person, but you end up invariably killing the person. You've killed the problem, but you've killed the person alongside. So the concept of the magic bullet was this. But the clinical reality is that for most of this time in healthcare, we have failed at this. What has largely happened is that instead of giving targeted attack, we've done carpet bombing. When a certain country wanted to bomb a target in our northeast, or was it northwest now? Probably northwest. And people in Kwara State were feeling it. It's not their country, so if he likes, whatever side of the political divide you're on, I apologize. But I just wanted to drive on that point. That if you want to kill one thing, I end up killing the most. You probably haven't done a lot. And this is what happens with chemotherapy in many instances, where we want to kill the cancer cell, but we end up killing the hair follicles. We end up killing gut lining. We end up making the person feel sicker sometimes than the disease itself. Well, this was all before you chemists made these amazing molecules. And now with your molecules, we can give heavy doses to the tumor and very low doses to normal cells around. And this is like a sniper. Instead of someone just coming to bomb everything, we can now, because we can elicit these targets at a molecular level, we can target them as well. And this is what radioligand therapy essentially is. That we can have remarkable outcomes with remarkable precision. And that leads us to a concept we heard about earlier, the theranostic principle. Now, if you keep your eyes on that word, it's easy to see that it is from two words joined as one: therapy and diagnosis. And this is very important because now we can see things with remarkable precision, meaning we can target them and treat them, or in essence, we see what we treat or we treat what we see. And it comes about by having a pair. One is a diagnostic pair, one is a therapeutic pair. And I want to think about it like this, and this is how I typically explain to my patients in my clinic. Think about a key holder that fits into a specific lock. And attached to that key is a light bulb. Just like that VIP convoy, it doesn't park anywhere. It goes right to the destination where it's designed for, stops there, and because it has a light attached to it, it can shine and tell you that there's a problem there. So that's the diagnostic pair. And now, what we're able to do is then switch out that light bulb and replace it with a bomb. But a bomb that's powerful enough to cause damage, but small enough not to cause damage beyond the place where you want it to cause the damage. So that's where the concept of targeted therapy comes. So use the same key to find the problem and the same key to treat the problem. And that's how we are able to do this. The other thing is that aside the fact that it gives precision, it helps you to predict. Because if the light bulb comes on in that patient, it already tells you that your treatment will very likely work in that same patient. And this is stuff we do already at the University College Hospital's Department of Nuclear Medicine. I'll show you for patient. I'll show you a quick case and tag this the Lazarus effect. This is a patient. Those many bright dots you see are from widespread prostate cancer that's no longer responding to any type of treatment. Previously, these kinds of patients will have been told, they're very sorry, we're very sorry, there's not much we can do, put your house in order, and yeah. And this patient, before he got to this point, failed surgery. I was telling my colleagues yesterday of a patient who had a surgery more than 10 years ago for 83,000 pounds. Yes, 83,000 pounds. He had it in Christie. And unfortunately, because molecular imaging wasn't available for PSMA at that time in 2012, parts of the disease were missed. The surgeons thought they cut everything out, but the disease was still present, and after a while, he stopped responding to conventional therapy. He went on to chemotherapy and failed that as well. And this same patient, because of the molecules that you have created, after a few cycles, look at how that picture has changed. You don't have to be a nuclear medicine physician to tell that something has changed there. You know the story of once I was blind, now I see. Once I was dead, now I'm alive. You can tell that something has changed. And with further therapy, look at what it looked like. His PSA decreased by over 90%. Pain, this man had his life back because of the molecules we create. Now, to put a few things in context, we have a few tools that we can switch around. You remember the bomb I told you about that you can attach to the key? There are two major groups we use. One is a little lighter. We use it more often. It destroys cells, but those cells have the capacity sometimes to repair. However, there are the kinds where is one touch and it's lethal. And to put that in context, if you had an accident, God forbid, with any of these two on your screen, both of them can potentially kill. You agree with me? I'm sure you know people who have been pedestrians who were hit by a motorbike and unfortunately lost their lives. But chances are that you can escape. But if the other one hits you, a certain poet said that masquerade, be careful, you are approaching the express. That's because these kinds of things can be on the express and can cause damage. But that's not where I'm going. Where I'm going is really that for us to use this powerful tool, we say we want to use the lighter one because this patient's disease is bulky, and the lighter one can travel farther, penetrate some more, give us better efficacy. Or the patient's disease is very small, and we want something that is very heavy but can't move far. Touches it a bit, kills it, touches nothing else. All of these tools that we can have as nuclear physicians are useless if the chemist's job is not reliable. If the stability the chemist gives is not there. Look at this link, this structure on your screen. A few parts of it that I want to point out. The one in red, think of it like a cage that holds this very powerful bomb. The blue part changes the way it is so that it can do different things. And the part in black is what is the tracker, the key that goes to find the keyhole. Each part of this thing is critical. Because if that black part is gone, this powerful device will just roam around the body and end up where you don't want it to end up and cause damage where you don't want it to cause. If that blue part is not stable, it means that this thing can go into the body as one piece, but detached. And therefore, we end up bombing where we don't intend to bomb. Or if the red part doesn't hold that thing in a cage till it gets to the destination and it lets it go, we're going to end up causing more damage to our patients. So this is why what you do should be important to every nuclear medicine physician. It makes me able to treat my patient with remarkable confidence, knowing that what I intend is what I'll achieve. So all the time you spend purifying that molecule, improving the stability of that compound, there's a human being's life that is benefiting at the other end. Some of the things in the future are that we're starting to see evidence that sometimes we don't even need to target the cancer cell itself. What we can do is target the support structure around it. Think about a wicked person on a scaffold who is climbing up the scaffold to go and cause harm, and you're not able to hit the person himself. What ideas do you have? Oh, look at how quickly it took you to figure that out. So one of the things we can do is attack the molecular scaffold with this molecule, and very soon, by God's grace, you'll be hearing that we got this done in UCH. So with this, and I'm sure Prof is already very well exposed to FAPI, but these are realities here, and the collaborations will help a great deal in getting us to these points faster. One of the things that we're also going to do in the future is, and I'm deliberately saying this to balance it out, okay? So that nobody leaves here and thinks that no, chemotherapy is a no. Chemotherapy saves lives. But what should ideally happen, and what I think is going to happen in the future, is a combination of these strategies, where what chemotherapy should take care of, chemotherapy takes care of. And what chemotherapy cannot take care of, more chemotherapy should not be given for that purpose. So that what radioligand therapy can take care of, then takes care of. So a combination of strategies. And with remarkable precision, we can be able to determine the dose that's ideal for each person and the dose that will be toxic for that person. So in coming to the end, I want to announce to us that the silo, each person in their silo, each person just doing their own thing, those days are gone. The silo is dead, and may it rest in peace. The future is us working together. So you, the radiochemist, creating those amazing molecules, and our team of radiopharmacists, coupling them together and coming to the clinical team where we see the patient. And this is a bit of a misrepresentation, to be honest, because we are the face of it, but there's a huge village getting this done, where after the patient is seen, administered the radiopharmaceutical that was prepared, Mazie Zima and his team image the patient, our nurses take care of the patient, our support staff make the conducive environment such that we can do what we do. The aim is for us all to remember that at the end of what we're doing is somebody getting their life back. And the future is us working together. So I used AI to create a picture that hopefully will be the picture of our future in treating patients, where it's all our voices coming together, all our best brains coming together, all our strengths coming together to give our patients a fantastic experience. Thank you very much. Thanks. Thank you so much. Okay, thank you. Yeah, so question one. Actually, I wanted to say we should appreciate our technical man behind the scenes. Thank you so much. So, question one, sir. Handling near misses. What happens when there's a near miss? For the sake of time, I wouldn't want to go into the depths of that, but that's something that the nuclear physician has to be prepared to deal with sometimes. If they say that you shouldn't go on a canoe without a life jacket if you don't know how to swim. That's the same way it is. You shouldn't give these therapies if you don't know what to do when things go wrong. Now, things can go wrong not because of the fault of one person or the other. Sometimes there are things that are not really in our control. So these things have happened in the best centers in the world. They have happened in centers locally. It's knowing what to do and picking it up as early as one can. But I should say that it could cost a lot to repair some of these damages. So that's why molecules that are resilient, especially in our own context, where, oh, sorry, you have 24 hours left in your house. I didn't. And in UI, I heard that there's power around the clock. And that's what I heard. That's what I heard. So this here is, if you ask me, sir, this here is the challenge to our collective community to build resilient molecules. Molecules that when NEPA takes light, the molecule 2 doesn't die like a television. So to me, I rather than it being a downside to us, I see it as a challenge for us to build resilient molecules. But yes, things can happen, but we're trained to handle those things when they do happen. Question 2 from Dr. Olojo, the role of biochemistry in this field is so central. Jokingly, I say to my wife that in the early days of bike, that's what we used to call it in med school, I used to think that this thing people are disturbing us with, I'm not going to use it in my life. Laugh out loud at me, because now I use it almost every day. Biochemistry is so central. This molecule that we talked about, fluorodeoxyglucose, is essentially biochemistry at work. It's essentially going through the Krebs cycle. Krebs cycle that I said, what I learned to use Krebs cycle for in my life. That Krebs cycle is what we exploit to make sure that glucose doesn't go through metabolism, but gets trapped because we change a hydroxyl group on it to fluorine. So instead of it going in and coming out, it goes in and goes in and goes in and accumulates. That's how we can see what we see. So biochemistry is so central. And who knows? Thank you, Mike. And who knows if biochemical pathways that somebody somewhere is despising is going to be the key to the next great molecule. So we look forward to collaborations. Question 3, Mr. Sunday. Thank you for that question. And I don't take answers like this lightly because they are people's lived experiences. To the healthcare professional, cutting off someone's breast is, you better let them cut it off. But that's somebody's, that may be part of someone's sense of self. Someone may be concerned that their husband is already behaving one kind. You now say cut off the breast, that could kill me. You know, that's what some people will say. But I want us to look past some of healthcare miscommunications in the past and look at the fact that many times, and for most diseases, and that's the truth, you need a combination of strategies. So if you had problems being seeded out from a central point, causing trouble in the head with a spread, causing trouble in the bones with a spread, you can tackle all of those sites. But sometimes, unless you take care of where the source is, you're going to be working in vain. So in some patients, cutting off that breast is the separation between them and death. So let's go out to educate our people that, you know, they said, let them cut off that leg. I know you're a person of faith, but let's hear what God gave the doctors wisdom to. Because some people have lost a limb and kept their lives. Some have kept a limb and lost their lives. Question 4, Mrs. Olabimpe, cost implications. Yesterday, I was speaking to a couple of students, and this question always comes up. Because something as wonderful as this, can you really reach? The truth is that it's not. It's not. And that's, let's take care of the elephant in the room. However, I want us to sort of change our concept. We many times think about cost in terms of cost spent. We don't usually think about cost in terms of cost saved. Think about the cost that will be saved by knowing the best answer the first time. Rather than having a less than best answer, taking a less than best approach, having complications from that, and then having to figure out what is going on. And by then, the problem has grown in military. I'm telling you the honest truth, and this is backed by science. You can look it up. It's the Lancet Oncology report on radiopharmaceutical therapy, where this was calculated in naira and kobo. Well, not naira and kobo, dollars, but in monetary terms, to show that these things, as expensive as they may seem, they actually save more money. Now, this is where my heart gets heavy, because I have worked in countries where these things, the patients, they pay that government covers it. In those places, it's easier to have this conversation. But here, when the person has to call Brother Lai and call NHIS can't even cover it, sir. Unfortunately, that would have been great, but it doesn't. You call Auntie Lai and call everybody to contribute money where it comes out of your pocket. So that's why strategies like what Prof has spoken about, where you can have pet-based work, but you can have spec-based work, technician 99 work, is a game changer, because it will bring these things that are available to now becoming not just available, but available and affordable. Because some people are excluded right now because of financial reasons, and that pains my heart every time. But because of the fantastic team here, some of these patients have been able to receive those treatments at remarkably low amounts because of their hearts and because of collaborations that have, covered costs for patients. So that's something to look at on the bright side. Production right now doesn't happen. No, radioligand production happens here because the coupling is done here. The isotope is imported. The peptides previously were always imported, now they're available locally. And very soon the peptides will be produced locally, because I know some very brilliant people who are in the house who have that passion. So my answer is in evolution. It's going to change very soon. Collaborations right now. Before we order radioligand therapies for patients now, it's already a multidisciplinary team meeting. You have the nuclear physicians there, the imaging scientists there, the pharmacists there, the nurses there. So there's that. But that picture that I put up was because it can be more. So right now we're not at zero, but we're not where we could be. So there's more ahead of us. And the final question 8, sir, as regards ligand's bioactive effect, is a simple answer. That in trace amounts and trace elements, they don't cause any effect at the site. It's really the radiobiological effect that we see, not a chemical effect that we experience. Thank you very much. Okay. But we'll have to connect this there. But my battery is actually what is my concern. Let's see what my battery says. Battery is 34% now. Okay. You can plug it in here. Charger, you can use a USB-C. So if you have a USB-C that can reach here. So what's the next one?
So what's the title? Until the done. Medicinal chemist. What's the title, please? That's what I did.
Yeah. So if we do this, okay, sure.
Sharing.
I think so. Yes, sharing. Yes, but you may need to charge it.
Once again. I hope you are enjoying the same workshop so far. Thank you very much. But before I go on to my lecture, let me just address the issue raised by the doctor, the biochemist. I believe that many of us do not have that opportunity. And those of us that have the opportunity, let's think outside the box. We are limited by the facilities that we have in Nigeria. That's limited our work, our research scope. So I want to invite all our students, all our early career sciences, please endeavor to aspire on a higher level and think of what you can do outside the traditional, research scope that we have in Nigeria. Because if you have the opportunity to go outside the country, you see that research has gone to a higher level more than what we are seeing here. So thank you very much. So now I title my talk. I won't take too much of your time because it's almost time to launch. Synthesis of radiopharmaceuticals and overview. Now, this is the outline. I don't want to waste time with that. If I have to be defining radiopharmaceuticals, by now, almost all of us know what radiopharmaceuticals are. What are radiopharmaceuticals? Medicinal products containing radioactive isotopes. Because I believe many of the students are just being introduced to this area. When I got the collaboration with Professor Franklin, many of my students were saying, Prof, this is a new area from what you are used to. How are we going to cope? I said, if I can cope, then it's to cope. So all of us, let's start reading. We are now what? Students. So now, primary uses is just to diagnose, that's imaging, for and therapy, targeted treatment, and you find applications in cancer, cardiovascular, and neurological disorders. Now, they act via radiation, not pharmacology. They enable non-invasive imaging and targeted therapy. You've heard most of these things. Key modalities are what? PET, SPECT, and radioligand therapy. There are also challenges, though. You can talk of short half-life, small quantities, and high purity requirements. Again, I'm telling you what radiopharmaceuticals are. In simple terms, you make use of radioactive isotopes. What are isotopes? Any students here? What they are taught chemistry. If you are a scientist and you not done chemistry before, raise up your hand. If you are in this, if you are a scientist, if you are a medical doctor, if you are a technologist, whatever you are, and you have not done chemistry before, raise up your hand. So I'm looking down. That's what I'm saying. So there's another, we call it linker, and the targeted molecule. So the target protein and the cancer cell. So these are couple radiopharmaceuticals. And you can classify them. We have the diagnostic radiopharmaceutical, like its gamma rays and positrons. Examples, secretional compounds for SPECT and the FDG for PET. Then we have the therapeutic radiopharmaceuticals. Emit alpha and beta particles, lutein 177 peptides, and the theranostics, dual diagnostic and then therapy. Now, how do you produce radionuclide? Presently in Nigeria, this is the difficult. I hope you are with me. But let's start from somewhere. That's why this sensitization training workshop is on. Let's believe that we can do it. Are you with me? Dr. Kolade talked about future scope and so on. If you have something in mind, oh, I want to achieve this, then you can look for means of achieving it. It's only when you don't think it that you don't act it. But when you think it and you act it, then you achieve it. Is that not so? Now, so synthesis of radiopharmaceuticals begins with the production of suitable radionuclides. Radionuclides are typically produced using nuclear reactors, cyclotrons, and radionuclide generators. I was fortunate to visit Dr. Ogunjobi's facility, and I saw some of this. On the second part of this training workshop, we still have that opportunity to. So Dr. Ogunjobi and Dr. Kolade, be ready to, accept us. Thank you very much. Now, chemical principles of radiopharmaceutical synthesis. Involves attaching a radionuclide to a biologically active molecule while preserving its targeting ability. This can be achieved by radiolabeling strategies. It could direct substitution. We all know substitution reaction in chemistry. These syntheses are simple chemical reactions. They are not something complex, so you should not be afraid. Isotopic exchange and chelation reaction, metallic radionuclides. Then you have the chelators and linkers, that influence stability and digestion. Then automation, synthesis modules, safety, and reproducibility. There is this case studies of this synthesis. Fluorinating fluorodeoxy glucose. Dr. Kolade talked so much about this. So this is the most common positron emission tomography tracer. Cyclotron production, then the precursor is mannose triflate protected glucose derivative. Then we have the radiolabeling, nucleophilic substitution. Students in the house, what is nucleophilic substitution? Students in the house, what is the nucleophilic substitution reaction? Are you hungry? Those please, let's remember this. Then we have the protection. These are drugs that removes the protecting what? Protecting groups. Then purification and quality control. That is using HPLC. What's HPLC? Clap for yourselves. Then in clinical, we have the tumor imaging, brain metabolism, and microbial viability. Now, there are emerging trends because science is advancing, like I said. Don't be limited by what you have. Stretch out your leg further. If you stretch out your leg, then maybe possibly that opportunity will come and you grab it. So we can talk of theranostic pairs, click chemistry, alpha emitters, and integration with molecular biology, antibody-based stations, and immunopets. Then when you talk of quality control, because there is nothing you do without QC, you can talk of radiochemical purity using HPLC, and so on, chemical purity, sterility and hypogenicity, pH balance, regulatory compliance, and so on. There are regulatory bodies that control any activities that is being done in this field. Now, our Professor Shoyinka has talked so much on the safety. It dwells so much on time, distance, and shielding. Please, no matter the knowledge that you gave from here, just, lay emphasis on it and keep it to use. Waste management protocols, personnel monitoring, and automated systems to reduce exposure. In conclusion, radiopharmaceutical synthesis, this is an interdisciplinary clinical, interdisciplinary and is clearly impactful. We agree with me that all of us, no matter your field, we still need that collaboration. It's a collective effort. And without one another, we cannot achieve our aim. So whatever your field is, you are all important. Now, it requires mastery of radionuclide production, labeling, QC, and safety. There is a growing role in precision medicine and molecular imaging. I'm a proud chemist. Clap for me. Chemists are central to advancing nuclear medicine. Clap for me again. Thank you. What do I mean by the whatever seeing the society in any school that what don't your life is being utilized society. So that we are by what the community and all. That's why you need to set an extra step. It's forbidden on your it's forbidden for the person to stand. It's responsibility. You know, now, then, yep. I think so. Imagine that time for you. Nigeria, I would say, you need to stand up and people going to stand doing that. I think so. As lecturer to be active, yes, and as lecturer I want to read this on what I'm doing. So, I'm starting with fast. Now, I thank you. Thank you so much for I began able to try it. And I'm working with really can help so much and put up that body. So so do I transfer this compounds now to break the gas? So because I'm only breast cancer and I'm targeting if the keep our recycle. And then I noticed some single parts based on my physical studies. So I want to link it up with these radio yes. So how can I go about it? Thank you. Thank you very much. Chemistry, but it's very involved step. You should go for the website. If you don't the correct and you know that you are getting a very good result, then you can now go for to do the website. So this is for you. If you know that if you don't get the correct answer and the results are good, then the next thing you go to the lab. Then there are some senators that can the activity. So it is the short same way. You don't do that. Next question. Thank you very much. All the comments. Yeah, it's short. Thank you so much for sharing all this. The problem was the comments is based on what the needs and wants to get. I want to hear first function and complete the that. Science so differently. When we are having changes like this, let's really posture. Really be acknowledge of some of them. So here's the goal. Area. Each one is something from the school. Wasn't something in farming was cheap in death. Or the COVID experience. It's the man. No, I think it's just speak. It's the meaning of that. No, it's what is simple in like rocks. And you have the answers. And you need to follow the plans. Then what it's useful in life to reach. So it's only those if the industry can become physically we have a proportion of that get therapy here, but invest in streets. But then they don't know so scholarship and I never share a story for you. Scholarship marks for so I'm very collaboration about this training. But this time I know we get leaders to come so that's not only there. The farmer that we have so you don't seven bread and yet yes, yet issues. And they told themselves, his life is a decision. They have respect. When you not you make the national policy
see treatment was. So there is a person. And like this kind of session about reflex on it. Of this was opportunities face. What? People are watching this. And I'm talking about you sit down. People are watching this. And you feel that they need to invite professionals in your place. And like, it's not, you know, it's like, it's not an as long you be shocked as the people this feels inside you that again. So listen, I believe there's something I have touched. It's that please I was letting you talk about thank you. My question is absolutely. Check of joy. I don't know. Objective somewhere else. So the so things on things what do you want to and so so prepare or keep I production of things outside of I'll let you. So that means so that's like the collaboration. Let them know that coming is called that coming back trying thank you. Sure. The companies, the medical and small we because we understand like what is the God. So if so we have our um, large sorry. Sorry. I think it's so. It's yeah, that's the time. You know, useful. So also kind of this in the watch capitalist. It's kind of machines. Sure. Yes. It's hard to manage this. It's all the way it's not that it's we this what's on there. We're rolling two. I'm gonna be out like six. So this way it's long 3D. What? Sorry, always very out of the watch. Let's see the function. Thank you very much. Let's see.
No, I wish you were on.
Oh, why did you? Oh, turn back. Back. If you say
It's 21% now. So
31.
yeah, it's gonna be power back.
Very slow.
Yeah,
But I think you said 33.
just 33 before. I think I
Thank
passed like it's charged.
Sorry, audience online. We are currently going for lunch, so you can also receive your own lunch virtually. So just assume, get yourself a very good drink, and the next few minutes we'll be back. I hope you have been enjoying the various lectures. It's been very, very fantastic and eye-opening. And we also love to welcome your questions. We have not been receiving questions. We want to be sure you're actually following us. So please, if you have questions, we still have some more workshops, seminars or talks to go. So please, if you have questions at any point, do not hesitate to give it back to us so that we can. And I hope the audio is quite better this time around. Thank you very much.
We got to what we did. Okay, so far. This is there. We don't want to keep on. So that was the next. So the top. So we were going to divide each row into two. And they said we have a don't be the one. So I was the so for this row, maybe for the whole one. Next. On one this base. So. There's something.
Outstation is a very strong station. No, you won't affect it. Yeah, we all know one kind of much. What needs? We actually is. What person you will set your guide you. Five, three, five. Station. You want value the decision of what you are on send it to us. Because this information is So such as universities, government, agencies, and so. Secondly, right?
And just leave. It's not working. Should work, but amazing. Okay. Yes. Sometimes running, just okay. Let's see. All right. How is staying so and all the shingles that are from Dr. Kolade, so this afternoon I've been speaking and spent with the pharmaceutical. So much has been said about what we can do, how we deal it, but I'll be speaking from the aspect and how we prepare. Something like they are companies in other words. Maybe on the last saying, we don't have any company doing that, but initially we prepare and go radio pharmaceutical, I don't have much time, so I'll just roll into slides. Please just go with me. Oh, okay. Oh. Don't worry, I'll use it to work. All right. The learning objectives is that I believe that when we've done, we would have understood what expected, what expected the pharmaceuticals and we would have been able to appreciate SPECT imaging technology in nuclear medicine. I believe we will know anytime the clinical application of SPECT in pharmaceuticals, then we and the rest of our current needs of the clinical SPECT in pharmaceuticals board for diagnosis and for therapy. All right, I'd just like to quickly define some terms. SPECT is a single photon emission computed tomography. So we're using with the pharmaceuticals, the radioisotopes now that will give up radiation in one single photon. There are some that will give double. And we leave other products to talk about until we're talking about pets. But this one will give up radiation in single photons. All right, so SPECT is a 3D nuclear imaging modality of test that shows how blood flows through tissues, organs, specifically highlighting metabolic or chemical activity. So that's what we're going to achieve with the radioligand or radiopharmaceutical. Then a radiopharmaceutical is actually a radioactive drug that is used for diagnosis of therapy in tracer quantities. So you're not giving so big a quantity that
leave where we want it to go and go to other places. And it must not have any pharmacological effects. I think the question was asked. So when we give, we're not expecting that to elicit any pharmacological effect. It's just meant to go where we want it to go, bind to the organ, or bind to the receptor, or whatever we're targeting. And the radioisotope part of it, because the composition of a radiopharmaceutical is the radioisotope and the pharmaceutical part, which is actually the ligand, which has affinity for the particular organisms. Look at the image. So it should not elicit any pharmacological effects. It goes there, attaches to it, and the radioisotope will continue to give off this stable photon of radiation. And that comes with a lot of information that the gamma camera will receive, and the computer will turn it into that we can now look at and know what actually is going in that form at that site direction. Okay. So let's look at an ideal radiopharmaceutical, what we expect it to be. It must be easily available. If that radiopharmaceutical is not going to be easily available, you have to order from maybe abroad and all that, and wait for days. The patient may even have died before the pharmaceutical comes. So an ideal one must be available. And so that's why we prepare the radiopharmaceutical inside our hot lab in the hospital. We have a hot lab where we prepare radiopharmaceutical. So basically, from that composition, I will show us the other time, we're adding the radioisotope to the ligand that has affinity for where we want to image. So it must be inexpensive and readily available in that nuclear medicine facility. So we can talk of the molybdenum technetium-99 generator that we use. We've talked about technetium-99N because, like we said, it's the workhorse of nuclear medicine. We can prepare a lot with it. It's an ideal radiopharmaceutical, and you'll see why. But it must be available. It must be prepared. We must get it out within the facility where you want to prepare the radiopharmaceutical. Okay, then the half-life. The half-life must be okay, such that when you prepare it, the complex you have can remain intact while we do all the notes, while we do imaging, while we do therapy and all that. So, and this technetium-99 has 6 hours, which is very, very good for what we do, because we prepare while we prepare a short activity, because if the half-life is maybe 2 hours, that means after 2 hours, if you say you have like 100 minutes, you just shut it down into 50 minutes. So if that's what you plan to do to your patients, then it's no more available. But because that 6 hours, we can prepare, inject the patient, and then scan. Within that 6 hours, then that half-life is applicable. So if you have any, and that's why pets with the pharmaceutical we talked about have very short half-life. It has to be prepared within the facility and quickly used. So, like I said, the short life must be the half-life rather. The half-life must be ideal. And these are other examples of other pharmaceuticals that have very short half-life. But with technetium-99 and 6 hours is okay. It's good enough to do what we have to do, inject the patient, scan the patient, and also get the results. And I agree with the pharmaceutical or radioligand that we want to use for the therapy of imaging and all that must have high tissue to non-tissue activity ratio. So we want it to stay in that organ that is targeted. But saying it's going to the heart, let it stay there. We must not be seeing it in the spleen, we must not be seeing it in all organs. And causing and exposing the patient to the necessary information. So the activity, there must be high target to non-target activity ratio. And so when we have that, we're sure that it's stabilized in that organ that we want it to be. Then there must be particle emission. So If we have the pharmaceutical prepared, we inject it and it goes into the patient and there's no emission, and there's nothing that. So that means the radioisotope pump is able to give off radiation because we need that radiation. The gamma camera, rather the detectors of the gamma camera needs to feed on that radiation to now make an image of that organ to tell us what is actually going on in there. So and there are different radiations that we have: alpha, beta, gamma, neutrons, and all that. We're talking of lead the other time is because for diagnosis, we prepare gamma rays. Gamma rays will come out of the bedroom. When we inject and goes to the organ of interest, it comes out. Beta rays doesn't move as far as gamma rays. Alpha does less. So we need the gamma rays to come out so that the detectors of the gamma camera can pick it. And one of the very thing that can stop gamma rays is lead. So that's why we need lead. We use lead in all that we do to protect ourselves. Even in our home, we have areas where we prepare and we use lead blocks. And those lead materials are always processed. Like we're talking of toxicity and all that, processed such that you're not touching it directly. And even in the blocks, they are well made, painted and all that, so that you're not getting to the lead. So the lead is not getting to you. So you don't have any problem. You don't have to worry about toxicity and all that. It's only when it has gone bad and you're still using it and it's exposed, then be careful. Okay, so there must be emission. And these are examples of alpha particle emitters, actinium. I won't bother us with that. I think when we get the slides, we can all look that up. Then let's look at the clinical uses of SPECT radiopharmaceuticals. The SPECT radiopharmaceuticals can be deployed, like I've said, for diagnosis and for therapy in the management of diseases, especially cancer. So technetium is the workhorse. We've said that roughly about 80% of all the diagnostic imaging in nuclear medicine, we can use technetium 99N to prepare a radiopharmaceutical. Its popularity stems from its ideal physical properties. I've talked about that 6 hours half-life, and the energy. This energy is very critical. 140 kilo electron volts. It's not too much, but will do the job. It's not so high that we are afraid and all that. But so that energy is appropriate. And apart from that, the real magic lies in its chemistry. So we'll quickly look at the chemistry of technetium-99M. Like we read before, it is made from a generator. This is a molybdenum-99 generator. You can have different ones, but this is a wet one that has saline already in this contraption. There is molybdenum that gives rise, that breaks down, that decays to form technetium-99M and technetium-99. So it's inside this contraption on an aluminum column. And once the saline goes into it, it washes out. When we put an elution vial on top of it, there's always a needle here. When we put an elution vial that is packed under pressure, the elution vial is packed under pressure. When we put it, it will suck out the desired volume that we want. It's 5 mils, 10 mils. It's based on the elution vials are packed like that under pressure to bring out a specific amount of the technetium-99M. And it comes out in the form pertechnetate. Let me remove. So in this state, this form, this pertechnetate form, it is very stable, but it's non-reactive. It's not really, it's non-reactive. So you can't use it like that because the oxidation state is +7. At this level, it's stable, but it will not react with anything. It won't react with our ligand. So we must do something to it. So to make use of it, we have to reduce the oxidation state. Usually we reduce it to either 5, 4, 3, 1 for some preparations by using a reducing agent. And the reducing agent we use is stannous chloride, tin 2 chloride. So it brings the oxidation state down to from 7 to 5, 4, 3. At this oxidation state, it becomes very reactive. So we can add our ligand to it. Okay, so it becomes electrophilic and it's seeking out that ligand. Once we had, it's almost like magic. And when we make sure we had under an aseptic condition. We're not introducing oxygen or introducing anything that is not needed. Water, no. Because if you introduce oxygen, it's going to affect the reaction. So this is the core of the technetium with this oxidation state. This also, let me read. So the target is to reduce it, bring it down to an oxidation state of 5, 4, 3, 1, then it becomes very reactive. Then once you achieve that, then you can add it to the ligands based on, like I said, based on the organ of interest or based on maybe the receptor site you want to target. Once it comes down to that oxidation state, then you can add. So you can have, so the general structure of radiopharmaceutical will be that, that it will have the core, then the chelator, it may be Mark 3, maybe DTPA. This is Mark 3, magnetite. Once you add to it, once you brought it down to that oxidation state, it reacts by direct chelation. And you can have the radiopharmaceutical you want, the radioligand you want. Like I said, if it's a peptide you want, if it's an antibody you want, you can have once it comes to that oxidation state. Okay, so let's look at some core the key cause of the 99 M chemistry. So we can have these oxo core, technetium 99 to oxygen like this with oxidation state 3. With this, we can prepare technetium 99 M Mark 3 for renal scan easily. So we can have something like this. I don't know if you're seeing it well. That's Mark 3. We can have this other core, dioxy core, with these 2 oxygens. Then you can see it in this radiopharmaceutical called 99M technetium HF power is used for brain imaging. Or we can have this core, nitrogen core, with a technetium bound to 3 nitrogen, like this. So it helps to prepare the pharmaceutical that we can use for myocardial perfusion, imaging of the heart. And we can also have organoleptic additions like lutetium 177 and all that to make with the pharmaceuticals that you can use to image and even treat. Like the lutetium 99, lutetium 177 can be bound to PSMA to actually image prostate cancer or to even treat. It's a theranostic agent. So it can be used to image and both treat prostate cancer. Okay, so these are other examples of radioisotopes or radionuclides rather now, or radioisotopes, yeah, that give off single photon of radiation. So we have iodine 1, 2, 3. There's the half-life, the energy, then what can be used for thallium 201 and all that, indium, gallium 67 can be produced from a cyclotron, or it can also be produced from a generator, just like a technetium 99M. Then xenon 133 is a gas. They all give off single photon radiation, so we can use it to prepare the radioligand. All right. Then there are some smart tracers, and Prof has talked about some of them, like this DART scan. So you're not just talking about labeling a molecule that would attach to the organ. Now you can also label molecules that would attach to receptor sites, that would attach to transporters, that would attach to peptides. This is one of them. So, and the chemistry that is that iodine 123 is attached to cocaine analog. I'm not sure if we are allowed to do that in the country. The cocaine use is very tiny. I've seen other ones that they use meth, they use heroin and all that. It's attached to the cocaine analog and it is injected and it binds to the dopamine receptor side in the striatum. So we can actually image and find out what is happening, especially in Parkinson's patients, because some may have tremors, like a patient with Parkinson's disease, but the tremor may not be because of Parkinson's disease. But when you have a scan like this, you can decipher to find out, is it coming from lack of dopamine in there or lack of dopamine transmitters in there and all that. And a normal scan will look like this. And the abnormal one will be shown from one of the presentations I've seen. It will either have two periods, that means just two dots. It should have commas like this, but you may have just two dots, or you may not see anything on it. Okay, you may not see anything on the scan. That's to tell you that, yeah, it's Parkinson's disease and all. Okay. Another one is this Octoscan, which we use Indium 111. This is also very good for imaging neuroendocrine tumors. So it is added and we can image and we can see all these images and the physicians can now interpret all that. So there is the ideal energy mix. There's the ideal energy that this radiopharmaceutical should have. And it's always between 100 and 200 kilo electron volts. So if you have a radiopharmaceutical that gives off radiation, gamma rays or single photon rays, and the energy is within this, then your shot will have a very good image if it's well prepared. So if you have too low, there's a possibility that as the radiation is coming, even the body tissues can take up that radiation so that it doesn't get out. So if it's lower than 100, so and our technetium-99M is 140, very, very nice. So you will see it on the scans. And that's called attenuation anyway. So you won't see anything. Nothing will come out from the patient and there will be nothing on the gamma camera scan. Then if it's too high, there's going to be a problem with that because the gamma camera has LED collimators that should provide a range where through the energies will pass. So if it's higher than that, then it's going to cause blurring of that image. It will not be clear. The image will not be clear at all. All right. So, like I said, technetium-99M, 140, even now the 123, 159 is still within that range. And so they're very good for scanning, for imaging. So you definitely see what you meant on the scan. Okay. I think I need to conclude now. So why SPECT? Because we've been talking about SPECT. But we've had PET, better imaging, higher resolution and all that. Why not go for the updated one and all that? But PET also has an edge and advantages. Number one is that it's available, especially for an area like ours, low and medium income countries. PET scanners are expensive. Cyclotron, you don't want to go near it, except the government comes in. They're very expensive. So spec tracers like technetium-99M, I've told you about the availability. You can prepare it within the facilities there. The generator is there. You buy the generator is there. Then you do an elution on it. You get the technetium-99M. PET scanners, like I said, expensive. Millions, multi-millions of dollars. Yes, half-life, isotopes generally last longer, hours to days, so allowing for delayed imaging. You can imagine PET. We have some PET radioisotopes that are 2 minutes, 50 minutes, 10 minutes. So, but for SPECT radiopharmaceuticals or radioisotopes, their hours are longer and you can do all you want to do within that time and you still have good results. Then cost, SPECT scanners are significantly cheaper. Gamma cameras are cheaper. At least we can afford compared to PET scanners. Double head, single head, that's what we use in acquiring the image from the SPECT radiopharmaceuticals. And they are common and they are smaller compared to the other ones. And it's something we can afford, like I said, in the low and medium income countries, like what we have in Africa. I think I'm done. Thank you very much for that. Okay. They should put it together.
Here's this first. This was happening. I did this well with twice. And let's say, you know.
Mention, okay, dozen, okay.
It was, you know, one size fits all, you know. Maybe something. You make it the house, we figure it so. That is price.
We'll say something in it. Okay. Station any lab within the country. So without any form of collaboration with any get some of this can be synthesized. Even say no. This mind was setting on health. I get in the short of it. And yes, possibly when the ultimate this problem something they got in your families. I don't know if it's like a social proximity or trust. I understand that with some of this, with some of the ability so some military system. So protection. You say some of this trust since they have functions with the particular settings. Also understand that there are also very details. So ever innovation takes its job into the system. How we have people show the specificity of the job is something that when it sits their culture and particular someone is trying without going. So people start to get to games through the issue of mistake. You understand everything around it. So, frankly, perfect. So sorry. I did get that question wrong because I thought you were asking because I thought it's for him, right? Because yeah, I needed to be sure. Eh?
He asked me, then he asked.
That's what did you ask me? That's what I want to be sure. Mhm. The lead is what? Sorry, I need to get that lead is what did you first say, please? It's good for. Oh, as a shield, okay. Okay. I needed to be sure so that I can answer this. Uh, you mean the generator now? No reactive generator. Okay. Okay. All right. The second question is, okay. Thank you very much, sir. I'm really specialized in aspects. I thought it's the one that I so until you are able to see the type of items, I decided keep the fast keep like he said that to take the potential man in achieving goals of this. Thank you. The first job is Sarah. So question so I'll pick that one. The first one is the person. Can you talk about this? Many reports. With approaches, and they come up with different things when they see position. There are empiric there are empiric applications of different doses. And when we really come to diagnosis now, if we want to do like a bone scan, there's an already empiric dose that is for bone scan for a 70-year-old person. So we're just going to tailor that activity towards that. If the patient is coming for therapy, that's another thing. It's going to be based on the investigations done with the scans that we've had from, if it's like maybe thyroid scan and all that, we've done the imaging of the thyroid scan. We can evaluate how big the thyroid, the tumor is. And based on that tumor, then a dose will be prepared for us. So what I've talked about is the pyrotechnics coming from the generator. Based on that, we need to prepare the pharmaceutical. And based on the empiric calculations already that existed globally, so we tailor into that. For imaging, if you want to image the renal and the kidneys, there's a particular empiric dose. So you tailor into that. If it's treatment, then it's based on what we see after we've done our tracking, looking at the patient, looking at the investigations that are done, then dosing the beginning for those sites. Okay? I hope we answered that. The next one is the synthesis about cocaine. I just asked when I was giving the presentation that I'm not sure it has been licensed in Nigeria, because I look at some countries where we take cocaine, we use it as a non-medical drug or something, but I'm not sure that's been done in the country. So I don't know enough. You have to learn where it is synthesized. I don't think I show anything, but I just brought that information to you. Microdosing, and we now have labeled it in India, or labeled it in how you want to do that. That's going to do. All right. Molybdenum 99. Somebody asked about molybdenum 99 that we did not stay in the body for long. You did. So we're not giving molybdenum 99. Molybdenum 99 is what we have that indicates technetium 99N and technetium 99. Those are the two daughter elements from it. So it's the technetium 99N that we get from the generator and we use. And the technetium 99N has 6 hours. So when we give our patient that for one time, once we prepare the medium pharmaceutical, we react with the MTP, methylene diphosphonates. It's going to attack with direct stimulation and we inject it. The patient don't work for maybe 2 hours. It goes all around the body and attaches to everywhere there is bone in the body. It has affinity for bone. MTP has affinity for bone. So while the patient is waiting for his or her scan, the patient will continue to hydrate, continue to drink water, and continue to go to the toilet, taking out the excess. And normally in calculation of radioactivity, if you have 5 half-lives, by 5 half-lives, 10 will not begin in the body, 10 half-lives. 10 half-lives of the 60 hours. So within 2 days, right? No, within 3 days. So you're not incubating. But let me say this. If the generator is not okay, and we don't do your QC, because once we look from the generator, we carry out QC on it to find out if there is any molybdenum breakthroughs. Maybe some molybdenum got into the 3799. We need to do that. We call it molybdenum acid. We have separate. And there's a threshold. Once it does not go above that threshold, then it can be used. If it's above that threshold, then we're going to discard it for that day. We're not going to use it. Because if we do, we're giving both 3799 and molybdenum. Inside the patient, the molybdenum will break down again to 3799 and molybdenum. So more exposure to radiation. Am I good? Metabolism. Somebody asked about metabolism that you need to get to the side of action to elicit your body. And that's why the ligand we're adding to the radioisotope has specificity for that organ, or maybe for the receptor side, or for the peptide. So it will not go to any other. That's why we added the radio isotope to it. It forms a complex. So once we inject it, they will go to the site of action. Except like the example of, okay, I didn't talk about this, but there's another PC that we need to do once we get the particulate from the generator. We need to check for aluminum breakthroughs because the molybdenum is an alumina sand. So there's a possibility of aluminum also getting into it. If aluminum gets into it, it's going to affect the image. It can make the complex break apart. So when we check and we find out that yes, there is no aluminum in it, that's when we do our analysis to the brain. Okay, so excretion and all that is no problem. If it's well done, it goes to where it should go to. And the radioactive part is decaying. Remember, there's a half-life, so it's decaying. And the lingered part, all the pharmaceutical part, like I talked about, must not elicit any pharmacological effects. The job is to take it to where we want it to go and attach. The radiation begins to come from that area. And we image and we get those money. And if it's therapy, so it's going to get there, it stays there and start radiating the tumor or whatever we want it to radiate. Are we okay? You asked about some pet lizards that have we tried to bring into specs? Yes, there's PSLA that was earlier being used with the pet radioisotopes. They label it with pet radioisotopes, but now in usage we've been able to do it. We label it now with technetium-99m, so that we can image for prostate cancer, because the prostate specific antigen can be imaged. So once we can have the preparation of the pharmaceutical to technetium, then we can image the PSLA everywhere in the body, not just the skin. Are you okay? Lead use. I told you the other time that the lead is always processed. Okay, so even the one that is going to be in the apron is processed, and you would have a material that covers it. And what lead does is it stops the radiation, doesn't allow it to pass through it. So it's not going to go through it and stay inside of it and all that. And you know, radiation, it has half-life. It's going to die off, as in it's going to decay till it's off. So it's like it's not going to stay in there and you now begin to touch it and all that. Yes. Then this for lead, no, we don't dispose lead, because what I've said is that the lead is processed. We have lead blocks that we use even in our hot lab. It's processed, painted, and all that. So that's how it's going to stay. It stops radiation from going, it doesn't go through. Okay, you're not giving it to patients. Do you understand? Maybe that's why you're mixing it. You're not giving it to patients. It's just one of the PPEs. It's part of the PPEs. And it's also part of the structural thing we use, because it has the ability to stop gamma rays. And I think I showed you from one of the, so it can stop gamma rays from going through. Okay, so you're not giving it to patients. It's just forming a barrier. And radiation is not going to stick on it and stay there forever. It's going to decay and go off. Are we good? Like he inhibits it from going through. Okay, so don't misunderstand it. I had a story at the time where I think it was 2 years or 3 years ago, where China was making some small toys with lead, and they brought it. I think they brought it over to Africa and all that, and some children picked it up, using it as toy, putting it in their mouth and all that, and those children got down with cancers. That's if you take it. These ones are not to be taken, and it has been processed. Like I said, if you see the one we use for the leg, it's painted. The one we use for the apron is inside another material. So you're not touching it. Okay? So let your mind be at rest. Are you okay? Like 3 more, they want to kill you. Generator waste. Okay. We do it in partnership with NNRA anyway, because they will come, they will check, you must record, open all your waste and all that. But at the moment, before they come or help us to dispose them of, especially for the molybdenum, or any other one that will not decay off in 10 half-lives, what we do is we have a waste room where we store it. No one goes there. So it will continue to decay till it becomes nothing. Once it has decayed, then you can now dispose it of as normal general waste. The same thing with all the needles that we use in preparing and all that. We keep it in the waste room. Depending on the radioisotope we use, depending on the half-life, it's going to decay. After 10 half-lives, you won't see it again. Then we can dispose it all as general waste. Okay. Then TC. On the first one. I'm sorry. Lingered research. I'm sorry, I can't get the last two anymore. Technetium 99. Okay, I think I remember. You asked that is there any other research on any other technetium 99 apart from the technetium 99N? Any other? It's always on molybdenum. It's molybdenum that will break it down. But I think plans are underway also to have to make molybdenum from a cyclotron, so that it will not just be from a generator. But there's still no, you can't have any other source because it's molybdenum 99 that decays to that. No other one will decay to. No other one will decay to technetium 99. All right, the last one, please. Lingered research. That's what I put there, but I can't remember. Okay. Yeah, now I remember. That's why we put up the chemistry. Once you have the chemistry, you can play with it. Structural activity relationship. You keep playing with, change, add some carbonite, add some methyl. Then that's what you do in the lab. Serious research lab that has money. Because when you do all that, you register for clinical trials. At least you start on animals, start on this. That's you can. It's a field that you can experiment. That's why I think this is very beautiful. Having this is lovely. So that we can wake us up and then we can. that's and so wants the G. And the goals not goals to manage. If you design a modeling, you and hope say ability, balance ability, it finds the times say ability as small for that. Affinity, that's affinity, that is fine for everyone else. Most importantly, we are stimulus to for energy. So what if you want a contract, you want to see a picture of that you value or really have that or not, but that's it. See a region and don't see other regions. So just make sure that we create for so it's part of it extend we get but certainly that is what so we can but extend the long way. Yes, the last lecture is going to be about working. And there are really off the value for media, let us appreciate. Yeah, presentations. No, I wanted to do this. Okay, okay. Logic. Once again, good afternoon to participants. I'm standing on the existing protocol because of our time, and I know we've been waiting since morning. Most of the things that are here have been discussed about, so we are going to be very fast with it. I'm going to skip. We all know that the pharmaceuticals, we know what they are now, and we know we have a technetium 99 radiopharmaceutical that is used for SPECT imaging, and we have a PET. The most important one among the PET is fluorinating FDG that is used for PET imaging. We've talked about ideal radiopharmaceutical. So we've talked about different types of radiopharmaceuticals. We have those ones that are used for brain imaging, thyroid imaging, lung ventilation, hepatobiliary imaging, renal scan, and what have you. We have skeletal imaging, cardiac, many of them, and we have therapeutic uses of radiopharmaceuticals. Among the popular ones, we have iodine 131, yttrium 90, lutetium 177, strontium, and samarium. We have tedium and the rest. Commonly used medical radionuclides. These are PET radionuclides. We have talked about fluorinating, carbon 11, oxygen 15, nitrogen 13, gallium 68. Fluorinating is very important because of this half-life, 110 minutes. For carbon 11, the half-life is 20 minutes. Oxygen 15, the half-life is about 2 minutes. And for nitrogen 13, the half-life is about 10 minutes. Gallium, the half-life is about 67, about 68 minutes. So those are the limitations. Because of that, fluorinating, because of this half-life of about 110 minutes. So it's like the workforce when it comes to, it's next to technetium-99. But the difference is that for technetium-99, it emits a gamma ray that can be seen only by SPECT
machine. So we call it gamma camera. So spectroscopy, we have spectroscopy in usage. And for fluorinating, it emits positron that is beta positive and can only be seen by PET scanner. So we would have been told that the PET scanner have a better resolution, than SPECT, but PET is more expensive. Like fluorinating FDG is about 1.6 million to do the scan in Nigeria, just for bone scan to see metastasis. And if you are going to use TC MDP, that one is just 200,000 naira. That's about 200 to 1. That's about 800% difference. The price, the gap is huge, and it's just for diagnosis, not for therapy. So we have some other PET radiopharmaceuticals. So basically, we use fluorinated, I think PSMA in Nigeria. That's PET radiopharmaceutical, but we use at UCH TC PSMA. That's what we use, because we don't have a PET. But in Lagos, that's where they use a PET machine. There's only one currently in Nigeria. We have some other PET radiopharmaceuticals like Dotatalk. We do TC99M Dotatalk for neuroendocrine tumor, FMISO, Falipride, FFT, Fluorbitaben, FES, FET, FCH, and fluoroacetate, many of them like that have been used. Radiopharmaceutical precursors, for fluorinating, to FDG, we use glucose. That's enriched glucose. That's why Dr. Kolade was telling someone that was asking about the role of biochemistry. The same glycolytic pathway, it will be trapped because it will not complete the pathway to form ATP. So it will remain there, and we can always scan it. But the precursor is mannose triplet, glucose metabolism. That is the idea. That's the idea behind the PET radiopharmaceutical. We have so many other. We do some things that you do when you are trying to label it. You precondition. You try to. The reaction is nucleophilic. We have been told that Prof was saying it, that nucleophilic reaction, SN2 reaction. And we do some acetylation, try to protect so that fluorine will not go to the wrong place. And usually, Walden inversion. That is what they use for aliphatic fluorinating substitution. But if it's aromatic fluorine substitution, we use a Wallach reaction. That's a SNAR reaction. Radiopharmaceutical in drugs development. So the most important thing when we are talking about drug development is that's what the question of many of us we have been asking. We are interested in how we can key into this area of development. And we are glad that many people are showing interest in the use of radiopharmaceutical in drug development. So the first thing to do is tracer development. So how do you do this? You design your tracer. You try to look at the strategy of synthesis. You develop synthesis of and radiosynthesis. Method of QC is very important. Individual evaluation, that's to check the biodistribution in animal, or you can do SPECT or PET imaging, but we don't have an animal scanner. So it's unethical for you to use human scanner for animal study. So definitely, as researchers, we'll be focusing on in vivo evaluation. Then data collection, and you do your interpretation. So quality control is very important because we want to be sure that the desired product is actually what you produce. If you do not have the desired product, it is not enough for you to say that you add a ligand to a radionuclide to give you the radiopharmaceutical. Some other byproducts may be along the line. So you need to check using a quality control method. So you check the physical appearance. Is it tubby? Is it clear? Check the pH to be sure that it's within normal physiological distance, usually between 4.5 to about 7, so that it will not be too acidic and it should not be too alkaline in nature. So isotonicity, use osmometer to do that. Chemical, Dr. Adiko, you mentioned about aluminum breakthrough, because the problem of the molybdenum is there. There is a limit to what is expected. Sometimes there may be some damage, so you need to use a strip to see there's no aluminum. Then you need to check what we call a molybdenum breakthrough as well. That is for radionuclidic. This thing, somebody was asking about molybdenum. So you check it, even he has explained using the molybdenum breakthrough test, or you can use the multi-channel analyzer, MCA. Radiochemical purity is very important. You need to be sure that the substance that the radiopharmaceutical, for most radiopharmaceutical for diagnostic, it is expected that the chemical purity should be 90% and above. But for therapy, it's expected to be about 95%, or even some will tell you 98%. There is zero tolerance for error when it comes to the preparation of radiopharmaceuticals. So we use ITSC and HPSC for that. And we have biological, this thing. Usually we don't carry a biological because of the time. You just want to be sure that the product is okay. So biological, that one, you leave that one for, maybe after. Usually we do some purification and filtration using the 0.2 micrometer filter to ensure there's no impurity, especially pyrogen. So, but it is expected that after you have dispensed, you have released, you can do toxicity, sterility, and pyrogen. So, of course, we know that sterility will not even come out because we need some days, hours before it will come out. That's my microbiological testing. But for pyrogenicity, there are some strip that you can use. You can use LAD strip, luminous mobile life release for that. Radiochemical purity of commonly used or prepared radiopharmaceuticals. At our center, usually we have your stationary phase, you have your mobile phase. Usually we use either one or two. Minimum, most of the time we use 2 mobile phase. And sometimes you can use 3 mobile phase. So we have polar and non-polar substance. For polar, we use usually acetone or saline. So we have TCMDP, DTPA, DMSA, pyrophosphate. That TCMDP is the most commonest scan that we carry out for metastasis in our center. We just determine, when you react, you can have what we call colloid. You can have what we call pre-particulate, because sometimes if you don't have enough ligand, so there will be some unbound particulate to be free, and you can have what we call the band complex, which is your desired product. So you need to find out among this, if it is, when you do your calculation, if you find out that it's below 90%, that means your preparation is not safe. The quality is not good because the labeling efficiency is poor. For non-polar, we try to change the mobile phase for non-polar. And for peptides, like PSMA, we are talking about 238, and even some for some molecules like chiconin, amygdalin. Those are medicinal plant substance extract. We can do that. Those are bioactive molecules, and those are the various mobile phase that can be used. So you now calculate your radiochemical purity. Use the unbound, that's the band complex, which is your desire, is equal to 100% minus the percentage of colloid and the percentage of free radionuclide. So when you remove from 100, whatever it gives you, determine the sources of your radiosynthesis. So radiochemical purity is most of the time for diagnosis, as I've said, is 90%, and for therapy, it's expected to be 95% or even 98%. About distribution of radiopharmaceuticals in animals for science, for researchers, follow the normal general protocol. After you have been able to synthesize, you will design your precursor, which is synthesizes, and you do your characterization. Usually I've met some people, we are already used to computational chemistry using in silico method. You get everything, then you dock it. After your docking, you look at the thermodynamically stable. If it's thermodynamically stable, you do the ADMET. So you look at the toxicity. So if it is good, then you can form so many other analogs of it, and you subject it to to software, so that you don't need to label AI has made things very easier for us now. So what you just do, after you have been able to get analog, you look at the score, you score everything, and you pick the best of all those your derivatives, and then you can now move to what we call radiosynthesis. So after you have been able to establish that, you label with technician 9. That's another area that we need to work seriously about, because it's not enough for us to just label and to go. We have been told that we need this agent to make precipitate to be reactive. So apart from that, you need to look at the pH, stable pH. You need to look at the buffer that you are going to add. You need to look at so many things, the temperature, factors affecting rate of reaction. You consider all those things together to be able to determine whether this thing is okay or not. If it's not okay, you check the desirability based on your RCP, your chemical. So to do that, you use a TSC method. That's what we use in our center because we don't have a HPSC. So the TSC method, when you do the count, you can count with a wet counter, or you can use your gamma camera to do the counting, or use what we call a radio chromatogram scanner. So when you get after getting your radiopharmaceutical done, the next thing is to now do the evaluation study. You look at, you get your animal. Usually, you can use mice or rats, for the study. So you anesthetize it, by peritoneal injection. Then you inject the pharmaceutical into the animal tail, because you need to first anesthetize so that the animal can be calm. Otherwise, you'll be able to, it can even bite you. And you sacrifice the animal by cervical dislocation. You can scan if you have an animal scanner, but if you don't have, you measure the radioactivity of each organ. After you have, dislocate, after cervical dislocation, you dissect, you get the various organ from based on the time, you determine your time interval to see how it will be distributed, in those various organs. You have your data and you interpret. So usually your organs, you have your standard in syringe. As you are injecting the same quantity of dose, you put it in the syringe, so that each time you are scanning, you are checking the one that's in the syringe. The one that's in the syringe is going to undergo what we call physical half-life, but the one that is in the animal, the one that you have harvested, where you have harvested the animal, that one will be both physical and biological half-life. That's what we call effective half-life. You determine it, and you determine your radioactivity, the one in the blood, the one in the liver, kidney, spleen, pancreas, bone. Then you now determine what we call the percentage injected dose and percentage injected dose all over the weight of that particular sample that taken. So the organs that you have extracted, you watch, right, weigh in the two before you measure. Your percentage ID is the activity in organ divided by activity in a standard. So every activity you measure, you divide with the standard activity that is in the syringe. You multiply to get your percentage ID. And a percentage ID over gram will be the weight of that particular sample that you have collected. So usually the activity is in a becquerel. That is the standard unit. One becquerel is equal to 1 disintegration per second. And there's another unit which is curie, millicurie. So 1 millicurie is 37 mega becquerel. So when you have 1 curie, it's just you multiply by that's 37 gigabecquerel, which is 3.7 times 10 raised to the power 10 becquerel. Thank you for listening. I have to rush because of our time. So if you have any question, you can now ask your question. So,
my question is, from the second countries that police
yes.
I wasn't the maximum solution. Yes. However, was given the source of the science. So the science where you have the same thing one of this.
Hope it's not too far.
Okay.
Ziti.
Yes, this. You said the bureaucracy. It's not like expect for each but now I it's like because it's like the appreciation of the people for updating presenting it's 100 minus key to find out something. So that's something is the reach. Let's say the one level one is in the past. You know, one is I like this video. And also, I was hearing easy or lyrical or mixed. This is
Okay. 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 Hope you are hearing me. So the what I was saying here, you are mixing up. Here we are calculating the radiochemical purity. So when you add your ligand to your radionuclide to form your radiopharmaceutical, so that radiopharmaceutical that you desire is your bound complex chemically. But there is the possibility that you may have some colloidal. You may have what that we call it colloidal hydrolyzed reduced complex, and what we call a free particulate because you don't have enough ligand to bind with. So those are two impurities. And to calculate the two impurities, you need to determine their movement along the TSC. It depends on their aggression, the mobile phase. And so for polar, using acetone and saline, I said that RF, I'm talking about RF, not dose now. It's at 0. That means for RF, for this particular number 1, TCMDP, it remains at origin. It's at origin. For free particulate and your band complex, both will migrate to the front, which is RF. Free particulate is to the front, RF of 1, where the RF of band will remain at complex. So you have 2 RF now at origin. So what we do is to calculate the RF of the free particulate. RF of free particulate all over total RF times 100 will give you the percentage purity or impurity of the free particulate. For the saline second solvent, you can determine the RF of colloid, which will remain at origin, but free particulate and pound will go to this thing. So that's why you need to add the percentage impurities, the two together. The RF, the percentage of the colloid and the free particulate. You will look from 100% to have your free band. Your bound complex. That's what I was explaining here. But for the other one, there are two different things. We are measuring the injected dose. If my injected dose, for instance, is 1 megabecquerel, that's what I've injected. I will now put it, it's a quality controller measure. So when you put it, you check it, you put the same amount in your syringe. So that means the exact amount in the same amount of volume. If it's going to be 0.5 mil, I will put 0.5 mil that contains 1 megabecquerel. Then also, and I will inject into the animal. So after 15 or 30 minutes, I want to check when I've already dissected and removed the organ. So I will check it at 30 minutes. What is the activity that is reading? So the one that is in the this is to standardize so that I will use it for all of them. So the one in the syringe, it will continue to decay down to the 6 hours. So imagine in a situation whereby I check the one in my syringe, it's giving me 1 molecule, it has reduced now to about maybe 500 something. Instead of 1, it has become 0.5 megabecquerel. And I now check the one that has been distributed, and it's giving me 0.6. I already know something is wrong. Do you understand? So that's why it's like your control. It's just like when you are doing, you are checking background. When you want to weigh, each time you want to weigh, you say, okay, weight of container before you have. So that's the way it is to us in a scientist, so that you will now have a comprehensive this thing to it. Mrs. Scotland, this is something.
What she's saying is that you're saying control. We have injected the drug. Our employment needs to develop the system. Your control should also be in the values. But I think where she needs to get into that, you're talking about physical apparatus.
And biology. Yes.
So the control is, I believe, is monitoring the physical apparatus, which was correspond what we are having for the progressively. So the decay of biological system was also matched the games.
Yeah, exactly.
It's different. That one is based on the happening.
That is effective half-life. We call that one effective half-life.
Yes.
The one in the animal is effective, but the one in the syringe is your physical half-life. So, but you now do the same thing for every one of them. Do you understand? To take care of any little error that must have occurred. Then sometimes you do it repeatedly. Usually, you have to do it 3 times. You have to do it 3 times. So that means you check for repeatability, or what we call reproducibility. So you do it 3 times, and you now find the average, because they will continue to decay. Each time you are doing it, it will continue to decay. How long does it take to prepare radiopharmaceutical? Is that is it the one we use or to do the research? Development. It depends on you. You determine it. So if you are ready to sleep in the lab, you have to sleep in the lab to get it up. But if you are not ready to do that, like for instance now, the tests.
Something is happening to questions.
Okay. So it may take like about 10 minutes. So it depends on how fast we have. So from drug development to the time that you have to go to clinical trial, medical guys to go that phase 1, phase 2, and phase 3. So it takes about 10 years to, but with AI is becoming more faster. It's becoming more faster. But just that's another thing. No, that's one issue. He's talking about me. It's a big God. It should take time. 10 years. So that, but for the point that we are talking about, so before you get to Dr. Kolade, that's the 10 million to get to that and look at the society. What was still done there? There is a plan on the city. The one issue. So can go to the clinic and get an number of the constant. No, after but for the other case, so South Africa dislocation. Normally there is what we call an ethical approval. When you are doing a clinical study, there's a good laboratory practice. So you need to apply, and all those issues will have been settled. But if you now want to publish, so the people that rejected, maybe all this Western world, they look at animal rights. They will say animal rights because how can you sacrifice animal? The best thing to do with that kind of people is to do the imaging. So there's animal pet city and animal pet scanner. So just put the animal, but it's very expensive. I don't know whether Prof, they have it in. So that means we need to go and see Prof and go to. But here in Nigeria, if you want to do it, there's no other shortcut because you need to. It's unethical. You cannot place the animal on the patient. This thing is not right. No clinician will allow that. So this is unethical. So you need to, the shortest way is to sacrifice and do that. And you not can't directly. But this animal scan is the best. Very easy. It's very easy. Just do your testing and it's even faster. The RF value. Okay, we have handled that. Why standard is to be answer that too. And is that all? Okay, that's Kuri and the husband. Yes, he developed radar, but Bectre, is the one that finished the work, and that's why SI unit is in Bectre. But some of us we are still used to Kuri. But when you are writing paper, you have to write in Kuri. You cannot bracket your military or whatever. But it has to be in Bectre. Another question. Okay.
Okay. Can I read the question?
Yes.
You see, for the pharmaceuticals now, they are always prepared in-house. There's no shortcut because of the half-life of the reagents that you are using. But for extemporaneous pharmaceutical, for those drugs that are very scarce, they still make them extemporaneous like doses, like pediatric dose that are not available normal. When you go to the pharmacy to get, maybe a child wants to take laces, for instance, a lower dose. You still need to prepare it extemporaneously, but it takes time. It's time consuming. So in the modern day, you want to make preparation very fast. So in advanced society, for the pharmaceutical, they have centralized the pharmacy, just like we have the normal pharmacy. That time, a clinic does not need to have an lab or the pharmacy in their hospital. So they can just send order. Tomorrow we have 10 boosters. They will supply them. By 10 a.m., 8 a.m. is already there. They just go centralized to the pharmacy. It's there for that. So there is no, and it's because of our population, modernization, industrial technology. So the era of experimentation, it takes time before you prepare it. Although we still do it for chemotherapy as well. All this chemotherapy, they still prepare it, do the mix. Even with that, it's if the number of patients are so many, it will overwhelm you. How many you can prepare at a time. But with automated where it can be very fast.
Okay. Okay. Thank you. Thank you very much. Questions and observations. And these sessions with our fields and to present what's not so. One, you have one. This one.
Thank you, sir. Yes, I think we can do it.
So,
It's a jackpot. So
well,
am I your attention?
knowledge of research and improvement. Also, it's not one, that's right.
So we put it near.
And then the scope of research reading was 80%. So those who gave the yes for the previous question was radio pharmacy, while 1% meant entrepreneurship. And then innovation, what innovation you want to bring to this area? 10% wanted to bring knowledge about chemistry. 10% wanted to reduce adverse effects on patients. 30% wanted cheaper, safer, and enabling to see the real pharmacists that again students and consulting. And then 40% wanted to improve knowledge of basic chemistry. And then 10% wanted to improve knowledge from the mental perspective. And awareness of organizations that support this area and increasing them. 4 participants had no knowledge of any such organizations, and then 7% and gave a response for yes, and then I A, and then cited implementing the research organizations. And then how can the government motivate researchers to embrace the skill in Nigeria? Because about training, very germane, about funding and facilities, and then sensitization, improving the cheapness and ability of this really schools. And then researchers and the group projected communications, presentation, policy advocacy, and I think more and more of this is very much.
I'd like to move on to the group 2. The rapporteur on the 2. Please come forward.
Okay, so
as I am and my inorganic materials. That means about having a computational bucket. Now, let's go. A lot of us, just like the reason why we are here is because, in a way, one way or the other, we have one thing or the other to have heard about nuclear chemistry. So in my group, I would say we have like 90% free knowledge. And that's why, because we really wanted to know more, that's why we are here. Thank you. The second one, we talked about what factors motivated you to participate in this workshop. Yes, a lot of us had that zeal, and that's why we're here. So we said a lot of us had, we want to know more about what chemistry, nuclear chemistry really is, to know the relationship between radioligand and the target. And we'll see that Dr. Mayowa really dealt with that. Thank you. And then the last part we have there is to know the purposes of the isotopes in treating cancer. Because we, like I said, I have a computational biochemist around me. I'm an inorganic chemist, which mostly I deal with transition metals. And most we know that transition metals they release a lot of radioactive elements and properties. Thank you. The third question is, are you aware of your institution's support for this area or this is the yes, because we have a lot of US students and participants amongst us. So we identify with UI and from Fountain University. So he also identified with his university. Now, he's not standing here alone. I am getting back at him. The fourth question has to do with, have you been engaged in nuclear medicine research? And that's why he's here with me, because we'll be wondering, he's just standing. What is he going to say? So thank you.
So based on that aspect, my university, where the collaboration with Civil University, it was implement through grants, through personal grants alone. And at the particular the ongoing also. So you don't have to make like pay and sex. They will actually use it to monitor the progress.
Convoca. Yeah.
It's not like but not expecting aspect and say. But I'm actually to determine to monitor the progress of the treatment of particular activity. For instance, after preparing the decision for a job, they go by deadline, but monitor the progress of the treatment. Just basically monitor the interaction between the lifeline and the particulars. Thank you very much.
Thank you. Thank you very much. Okay, so then we go straight to the innovations. Some of the things we said had been said by the first speakers, which we also agreed with. Then we also mentioned, now we diversify. We have been talking about molecules, imaging, and all the likes. There is this particular part that we discussed in my group. Now, it is because there are a lot of radiations around. That's why a lot of people are coming up with a lot of radioactive infections and all that. Now, as a material chemist, and I'm into a collaboration that has to do with the use of these our waste into how do I put it, a manageable composites, manageable materials that will help eradicate some of this waste. And if we don't have so much exposure to radiations in our environment, how come, even as far as we have it will be limited to treatment? Thank you. So, and every other use. The seventh question, are you aware of organizations that support this area? Yes, we mentioned a little, because part of us, we had a participant that works with the Society of Nuclear Medicine and Molecular Imaging. We also have International Atomic Energy Agency. We have participants amongst us who are, how do I put it, employees of these institutions. And the last one we have there is International Center for Precision Oncology. Thank you. So those are the three ones that we were able to write. The last one, sorry, I'm taking time. What do you think about the government should do now? We listed three things. We said government should invest in the availability of radioligands, just like we were talking about that. What is the government's involvement? So they should invest more. They should help subsidize treatment. Most of the things we talked about is when there are available diagnostic machines. For example, if I say I want to go into the hospital. Sorry.
I would like to call the rapporteur for group. Hey, bring it. Yes, ma'am. Thank you. Thank you very much. I would like to call on the rapporteur for group 3. Yes.
Group 3 minutes.
Group 3.
What time I thought?
Good afternoon, everyone. So from group 3, I'm answering the first question, what is your level of pre-knowledge in nuclear medicine? And we are 15 in group 3, and only 4 out of 15 have basic knowledge, a percentage of knowledge in nuclear medicine, and so only 1 out of us has advanced knowledge in this nuclear medicine. So the second question, what factor motivates us to participate in this workshop? We have numerous answers here, and one of them is knowledge to close the research gap, and just to be aware of this radioligand that we talked about. And another one is to venture into cancer research, and many more answers. Also, the third question, are we aware of our institution support for this area of discipline? And majority, we're not aware. I think it's only 1 person that is aware of the institution support for this area of discipline. About the question of have we ever been engaged in nuclear medicine research? Majority says no, and only 1 have been engaged in it. So if yes, what scope? And the part of the person that is engaged in this form of research is one of the members of the team that started nuclear medicine in Nigeria in 2006. So are we aware of organizations that support this area? No. And the hindrance that we see, maybe this is something that is hindering us from venturing into this form of research. We talked about funding and not knowing how to go about it. And what innovation do we think government should put in to motivate researchers? We talk about funding. We talk about access to radioisotopes. We talked about facilities, well-equipped laboratories, and well-functioning equipment, and legislations and policies to help motivate researchers.
Many thanks. I would like to call on the rapporteur for group 4. Group 4. 5. Group 4. We are the members of group 4. Please put up your hands. Group 4. All right. Group 5. All right. Group 5, please come forward.
Okay, thank you. So for the first question, level of pre-knowledge. So we have about 10%. The remaining 90, they don't have pre-knowledge about it. Factors, yes, pre-knowledge and for certification, if possible. Then awareness of institutional support, yes, just a few people have that awareness. Have you been engaged in nuclear medicine research? No. And so that automatically disqualifies question 5 because there's no one in our group that is engaged in nuclear medicine research. So for the 6th, innovation. Okay, someone mentioned about introduction of nanomaterials when we talk about delivery of the drugs or into the body system. So if they can use nanomaterials for easy delivery. So someone mentioned that. And someone talked about waste control, talking about cancerous or carcinogenic products being used. So that area. Aware of organization that supports this youth? No, nobody in our group has that. And then the government should do. Okay, this one might go to maybe some of our professors. Because of, if we tell the government to do anything, somebody who is not in academics, who does not know the rigors and the amounts of money involved, they might not really understand or carry the weight of how much money goes into research. So if you can have people in academics also maybe venture into politics, not fully, if they can be affiliated with some of these political parties, so I think they mentioned the lack of funding, talk about free scholarship, because to be able to do some of these things, you need money. You can't be performing research and still be working. You even use 20 years, like this. Thank you.
Thank you very much. Group 6, please.
I want to write this, so I'll bring it.
All right. I'll just listen.
Good evening, everyone. My name is Alison Mbike, and I'm representing Group 6. So for the first question, what's your level of pre-knowledge in the nuclear medicine? I think we had one person who had vast knowledge in nuclear chemistry, and we just had one person with average knowledge in nuclear chemistry, and the rest member of the unit had zero to little knowledge in chemistry. That's the chemistry nuclear medicine, actually. What factor motivated you to participate in the workshop? A good number of persons were intrigued by the theme of the workshop. And then I think 2 persons found it aligning to their long-term goals, which is, I'm one of them, the other person aligned the workshop to their long-term goal. Then some other persons came to learn and to be exposed to knowledge about medicine and what it involves. Then are you aware of your institution support for this area or discipline? For this to be happening, I think the institution or the department is in support of this, and I know we know it's gonna continue after now. Have you been engaged in nuclear medicine research? I think we just had one person who is into that field, and I happen to have should I say an average knowledge about it because my supervisor, Professor Oluide, got into it with Professor Franklin, and we're asked to read papers on it, and we attended the training in UCH about it. So I think my knowledge about nuclear chemistry and radiopharmaceuticals started from there, and I think I'm loving the concept. Yeah. Have you been engaged? Okay. If yes, what scope? I've just explained. And the other person who is practicing has a vast knowledge about it. What innovation do you want to bring into this area? I think basically we talked on the suggestions. It might not be us, but I think what the institution and what I think the country can bring. First of all, is translational research. We should be able to connect what we're learning into the society. Also, we address the gap, industry placement. We do not have industry placement. A lot of this knowledge is not going out there. We also suggested that if radio tracers linked to SPECT can be made available, like the one used for PET, if there's a way it can be modified to be used for SPECT. And it's a lot of readjustment to the whole system, but it's a research that can start to make it accessible, low cost, and affordable. Then training students as an addition for academic knowledge. So those are some innovations that can be brought into this. Are you aware of organizations that support this area of field? We have IAEA. We also have World Association for Radiopharmaceuticals and Molecular Therapy. We also have CDION Foundation. Lastly, what do you think the government should do to motivate researchers to embrace this field? I think basically is to support and build policies that will help, because some of the researchers we know want to really do this, but they are constrained by resources and the approval of this. So we can intimate them, create awareness on the importance of this, and see how policies can revolve around this. Also, behavioral modification can be infused into policy making. I think that is that from Group 6. Thank you very much.
Thank you very much, Gab. We want to sincerely appreciate all participants for our tenacity since morning. And going forward, I have one or two information. The Google Drive of all the resources shared in this workshop will be shared with us. So please let's make sure we drop our email addresses. And also, I think there is a mix-up. Some people feel that we still have another session tomorrow. The next session will be on the Monday. 2nd day of March. at UCH. So it is not tomorrow. Thank you very much.
Ladies and gentlemen, let us appreciate ourselves. Let us clap for ourselves. Let us do something. Can we react oxygen with magnesium and say, oh my God? On this note, let me call on Dr. Ogunjobi to come and give votes of thanks, and we bring the program to an end.
I really want to appreciate every one of us for being part of this workshop. I'm really glad to have many of us here, and I hope you're coming. Has not been in vain. This workshop has been impactful. It has been educational, and we have received a lot of information. So just as we have been told, we are not going to have one tomorrow because Professor Franklin will be traveling. So we are going to, the second day will be March 2nd, and it's going to be at the Department of Nuclear Medicine, UCH. We will communicate with you to send you a mail. That's where we are going to see the facilities. All these things we've been talking about is more of theory. So we are going to now see the facility. What does the facility look like? All those things we've been mentioning, the generator, the spec city, you are going to see them live. When you come. No worry, we are going to ensure that when you are coming, you are not, it's not to be cold. We are not going to work. It's not going to be hot. Even though we said hot lab, it's not going to be hot because we are not going to work on that day, because those are part of the ethics of nuclear medicine practice. We ensure that you don't enter into a radioactive environment when we are working. So once again, I want to say thank you for coming. And I say, as we go back to our various places, the Almighty God will take us back home safely. Thank you. Thank you. Okay.